note that I put up on the top, if you see a base unit in the problem, so that means if one of the units is meters, liters, or grams, then it's just one step. So it's only going to take you one step, one times in a line in order to get to the answer. So you just put the given unit times, put the given unit on the bottom always. And in this one, the answer unit, it just goes on top. That's all you have to do. You just have to remember what the ratio of the prefixes mean to the base unit. But if you have two prefixed units, so that means if the given and the desired units both have prefixes, they both have kilo, centi, deci, milli, micro. If you have two prefixed units, you can still just remember what each prefix unit means regarding a base unit. Just do it in 2 steps. Okay, so in that one, with the 2-step process, you're going to go to the base unit first and then go to the answer unit. So it's never more than 2 steps.
So that's how you know it's a 2-step, it's like a centi.
Yes, so like the first one, kilo and deci, it's 2 steps.
Okay, because that's where I was getting confused about how
If you see liter, meter, or gram all by itself as one of the units, it's just 1 step.
Okay.
So like in this one, the very first one, so you have milliliters and liters. So we could do that in 1 step. Okay. So we had the base unit liters as one of the units in the problem. So if you have a base unit, it's just 1 step. But if there's 2 prefix units like the 2 on the bottom, then you know you're going to have to go to the base unit first. But the thing is you really only got to remember those, what does kilo mean, what is deci, centi, milli, and micro. Those are really the only ones that you have to remember in order to be able to convert. So with this one, kiloliters to deciliters, kilo and deci, we've got to do 2 steps. So we're going to go from kiloliters to liters and then liters to deciliters. Okay, so you're just going to go the base unit in between each time. And that way you don't have to remember anything except those 5 and what they mean in relative to that base unit. So you always start off, put down your number, 24 KL, times in that line. The unit you start with always goes on the bottom in the first step. So KL goes on the bottom and liters goes on top, because that's what we're going to do in that first step is we're going to go to the base unit. Now kilo is the one that's unique because kilo is 1,000 times larger or smaller? Larger. So kilo gets the 1 and the base unit gets 1,000. With all the other ones, deci gets 10 in front of it, centi gets 100 in front of it, milli gets 1,000 in front of it, micro gets 1,000,000 in front of the prefix. But with this one, the prefix gets the 1, and it takes 1,000 base units to make a kilo. So remember, like a meter is this long, but a kilometer is almost a mile. It's about 0.6 miles. So kilo is a much larger size, takes 1,000 base units to make a kilo of anything. But that's going to let us then get rid of that first unit. And then we're just going to do the second arrow. So now we've got liters, and so we're just going to do 1 more unit conversion times in a line, and that'll take us to what unit goes on the bottom? Liter on the bottom, and then on top, deciliter. And in that, whenever you see deci, what goes in front of it? 10. Oh. Liter gets the 1. So liters and liters will cancel. Now remember, in doing this math, just multiply everything across the top, and then you divide by each thing that's in the denominator. So it'd be 24 times 1,000 times 10. Exactly. But setting it up this way and following this units really helps you to make sure that you actually put your units in the top or the bottom. Because when you get done, they should cancel. If you get done and you have liters and liters on top, something's not right. Okay, then you know you've got to go back and look at how those units are set up, because units should cancel, so that the only unit left is the answer. So micro and centi. So we're starting with micrograms. We're going to go to what first? Grams. And from grams, then we can go to centigrams. So because we have micro and centi, 2 prefixed units, you want to go to the base unit in between. Put the unit you start with on the bottom. Unit you want to go to in the first step is grams. Micro means a million. Whenever you have micro, that's the funny U. If you have micro, you're going to put a million in front of it. And then when you go to the second, the unit that you have now is going to go on the bottom. So whatever the unit you put on top, the base unit that you put on top in the first step is now going to go on the bottom in the second step, so it'll cancel. So that will put centigrams on top as your answer. Whenever you see centi, 100 goes in front of it. So multiply everything across the top, 97,123 times 100, and then divide it by a million. When doing the unit conversions, don't round or anything, just keep that number. 9.7123. Here, milligrams, decigrams, two prefixed units. So you know you're going to do it in two steps. You're going to go from milligrams to grams. And then grams to decigrams. Anybody get a number? 0.14. Everybody get that one? All right, so there's the setup for it. 14,000 on the bottom in the first step, 10 on the top in the second step. 14 times 10 divided by 1,000. And go back, you can see that your units will all cancel. So it leaves you with your answer of decigrams. So I encourage you to practice these, because the more you practice them, then the more you just see that pattern, how you set them up each time. It doesn't really matter what the prefix is. You always start off and you're setting the prefixes up or setting up these units so that they'll end up canceling, so that you can work your way to the answer. With metric though, you can convert with anything, and it's never more than 2 steps, because you can always just go to a base unit and then go to the answer that you need. So just remembering the ones that I gave you previously, the ones here, what the kilo means, what deci, centi, milli, and micro. And those 5 are really the 5 that we use the most in this class. There are other ones, but we really don't use them as much. These are really the most common ones that you'll see used in medication and dosaging. There are some English to metric units that you use pretty consistently that we'll talk about along the way. So from that, we then went on into significant figures. So in significant figures, that's really just being able to look at a number and determine what numbers were measured and what numbers are just sort of estimates. How exact is a number? Because that's important when you're trying to figure out how to round these answers that you come up with. So one of the rules, rule number 1, all the numbers that you see between 1 and 9, they're significant. They're considered measures. So 1 through 9 are always significant. So if you see, well, if I just spell the significant, So if you see 1,233. So that's number means like you measured 1,230. 3 might be your estimated number, but that's still considered a measured value. So all 4 of those are considered measured and significant. Any number between 1 and 9 is considered a significant number. The real challenge just comes in with the zeros. So the zeros are the ones that you're like, are they really significant? Are they measured? Or are they just telling the size of that number? And so with that one, the 4 rules with zeros. So zeros in front. So if you have a decimal place, zeros in front, they call those leading zeros because they're leading the number. So if you see zeros in front with a decimal, they're never significant. If you see zeros at the end of a number with no decimal, they are not significant. So zeros in front, zeros at the end with no decimal. And the reason for this is really like if I go to scientific notation that we're going to talk about in a minute, when I change this to scientific notation, I would say that this is 2.5 times 10 to the negative third. I would drop those zeros off and I'd only keep those significant numbers, the 2 and the 3. So that's like part of the reason they're just holding how small that 25 is, the relative size of it, where the decimal place is. Same thing here, we said with 12,000. So you say like, I think I have 12,000 pennies. You don't know if you have exactly 12,000. That's really an estimate. So the 1 and the 2, you know, are close, but the zeros are really just indicating powers of 10, how much larger it is. But if you have a decimal place, now your zeros at the end become measured. So zeros at the end of a number, if there's a decimal place, those are considered measured numbers, and you keep those. They're going to add into significant figures. And then the other one is if you see zeros in between. If you have a 0 in between non-zero numbers, then that's considered a measured number. So it just happened to fall on the 0 when I did the measurements, so those would be considered significant. So we went through a number of them and trying to figure out how many each one is. So do go back and double check with those ones, but it's really the zeros. I put zeros in every single one of these examples. The zeros are the ones really that always end up causing the trouble. So if you had 4,201 milligrams, how many significant figures would that be? 4. So the 4, the 2, the 0, because it's in between, and the 1, all measured values. What about 0.68902? Be 5. The 0 in between the 9 and the 2 is a measured number, but the leading zeros would not be. So this one will be 5. It doesn't matter if you have a whole lot of zeros in front. 0.000031. 2, right? Leading zeros, even if there's a decimal, leading zeros like 0.68902, you said that 0 was not significant. So it's no zeros out front are ever significant, okay? So this one, just 2. Leading zeros are not significant, and 12 million, just the 1 and the 2. Lagging zeros are not significant unless there's a decimal. Okay, so zeros at the end, the only time you count those are ones if there's a decimal place present. Okay, so just with those zeros, and we'll keep on talking about them and we'll use them throughout the entire semester because it comes into place when you begin to use this in math problems. So when you have measured values in math problems, you have to round, but your rounding is going to depend with multiplication and division. It depends on significant figures. So when you multiply or divide 2 numbers, the answer needs to be rounded to the smallest number of significant figures in the problem. And that, I mean, it kind of makes sense. So your answer can't be any more exact than the numbers in your problem. That's sort of the rationale or reason for that. So I gave you 67.893. So that has how many significant figures? 5. All non-zero numbers, there's 5 significant figures times 2, which only has 1. So your answer can only have 1 significant figure. That doesn't mean that your answer is only going to be like a single unit. It may have lots of numbers, and you may have to add zeros to indicate size, but you're going to round, so you only have 1 significant figure. So in that one, we ended up getting the number of 135.786. Okay, so that's how many significant figures? That'd be 6 of them, okay? So we're only going to keep the first one we come to. So you're going to keep the 1. That means that the 3 is the next number, and we're going to have to round. So if the number is 5, if it's lower than 5, you do what? Round down, okay? Above 5, it means the last significant figure will round up. But this means that the number that gets dropped, the 3 and the 5, 0.786 is going to get dropped. But I'm not just going to put 1, because my number is 135. So I have to keep the zeros. I have to put my answer as 100 with 1 significant figure. The 1 in 100 is significant, but those zeros need to be there because they hold the size of the number. Okay, so if your number is not on the single digits, if it's in the hundreds or tens or millions, whatever, you've got to add those zeros in to keep the size of the number.
So I'm not trying to sound stupid or anything.
Not at all. Go ahead.
So if that was a 5 there instead of a 3.
So if it was like 155,
Yeah.
then I would round it to what?
Would it be 200?
Yeah. So then instead of, I would then round the whole thing up, still keeping 1 significant figure, but now the answer would be 200. Okay, so 200, no decimal place on the end, only has 1 significant figure. Okay, but I keep those zeros because it's indicating the size of the number. Okay, so some that we started working on. So look at this one. Since this one's a multiplication division one, and this one. So work these two. First, remember, you do the math, don't round, then figure out what you have to round it to. Reese came in, Shala came in. Does anybody need a calculator? Does everybody have one? Or your phone, either one? Okay. This one, 0.176171875. Yes? Did I put it in right? 0, 6. Yeah. So you get all of this. And this is like, if it doesn't come out being like this perfectly even number, this is really common to get this. You get a decimal place and you get all of these digits up to 10 digits, but you can't keep them all. Okay. So 0.176171875, I need to round. So you've got to look at the problem. How many significant figures in this one?
No. Oh, no. 3.
5. 5. Which ones? The 451 and the last 2 zeros. Remember, lagging zeros, if there's a decimal, then they count in. Okay, so in this, the 4, the 5, this 1, and the 1. So there's 5. Okay, what about the other one? 3. Leading zeros are never significant. Okay, so this has 3. So that means that I need to round to 3 significant figures because that's in the smallest. So I start from the left. Now the 0 out front, is this going to count? No, skip it because remember, leading zeros are never significant. So that means this 176, that's the first 3 significant figures I get to. So then I draw my line. So I'm like, okay, I got to do something with all the rest of it. So the next number is a 1. So what will you do? Just drop it. Okay. So since the next number is a 1, that means all those will just drop off and I will just leave my number as 0.176. Still keep that 0 out front because it's holding the size of the number, but the 1, 7, and 6 are my 3 significant figures. All right, so now this one, 1 million times 12.56. Yeah, because there's a decimal. So as soon as you put a decimal, any zeros at the end, and it doesn't matter if it's zeros in front of the decimal or zeros after the decimal, like I could have 10.00, that would be all 4 of those would be considered significant. If there's a decimal, any zeros at the end are considered measured values. So in that one, I have 7, and then 12.56, 4. So in doing this, doing the math, right? 1, 2, 3, 4, 5, 6. Yes. So adding these in, 12,560,000. So what would I do? The whole thing stays. I'll just rewrite it so it looks like a normal number. Sorry. So you did the math. I get 12,560,000. If I don't add a decimal place to the end, all those lagging zeros they're not significant, but they have to stay because they keep the size. I don't want to go from 12,560,000 to 1,256. That'd be a really big price cut. That would be a whole lot smaller. So you want to make sure that you're keeping the zeros either in front of a decimal place or zeros at the end of a number if it's bigger than 1 to make sure you're keeping the size. So here stays the same. Now, addition and subtraction, they don't go with significant figures. They go purely based on the number of decimal places they have in common. So in this one, you look at the number. The answer should have the same number of decimal places that are common to all the numbers in the problem. So if all your numbers go out to the 10th, one might go to the 100th, one might go to the 1000th, but it's the one they all have in common. So in that example, the 2, which would be the hundredths place, all 3 of those numbers have that in common, and that is why I would round to 2 decimal places. So that one, you really don't care about the significant figures. You're really just looking at decimals. And if they were all to the ones place, you would round them all to the ones place. Okay, so if 1 was 12, if you had 12 and 0.02 and 1.98, and I was adding them all together, if I was adding them all together because 12 is just a whole number, I would round my answer to a whole number, okay? Because that's the smallest unit they all have in common, would be at the ones place. So in these, so do those other two, 25.896 minus 15.7896. Do the math first before you decide to round. So in the first one, I got 10.1064. Can I keep all of them? No. Okay. So what do I have? What's the How many decimal places out that do they have in common? So this one, 896, this one's 7896. So that means 3 decimal places is the one I have in common. So that means anything past, I'm going to round, that's a 4. So what do? Drop it. Okay? So that would be 10.106. And then the last one. 9655.82. So you're going to go to 1 decimal place because 1 decimal place they all have in common. So that means I'd keep to the 8 and the next one's a 2. So you would just drop it off. So it'd be 9,655.8 in your answer. So we will talk about those rules and go over them, especially as we do math problems throughout the semester. These is really when you're talking about measured numbers. When you're doing unit conversions, you don't round. So if that number has 8 digits, you just keep it, okay? So you still keep those numbers. Don't worry about rounding when doing the unit conversions. Scientific notation is another thing that you're going to see. This is a way of making a really, really big number much more manageable, making a really, really small number look a whole lot more normal. So what it is you put any number between 1 and 9 by moving the decimal place to the right or to the left, and the number of decimal places you move is the number that goes in the exponent. So when talking about really, really small molecules like atoms, you may need to have billions and billions and billions of them in order to have an appreciable amount because they're so small. But writing this down every single time you're trying to take notes, you're like, geez, trying to keep track of the zeros. So putting it in scientific notation allows you to like shrink this number, fit it on a page, work with it a little easier. And the trick here, you're going to take and move your decimal place until you make your number between 1 and 9. So it's always going to have a single digit in a decimal place and then whatever comes after. So in this one, I always start and then just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 14 zeros, but I got to keep going until I get a single unit. Okay? So what did I say, 14? Okay. 15, 16, 17. So this would be 6.203 times 10 to the 17th atoms. So that exponent tells you how many decimal places. If the exponent's a positive number, then you know this is a huge number. This is a number greater than 1. So if you have to move your decimal place to the left, exponent's going to be a positive number to express it in scientific notation. But then when you're talking about like how much atoms actually weigh, you can be talking about super, super, super small. Like you can't weigh this. This is like theoretically. So scientists have sat down and said, well, if we calculate how big an atom of this is, it's something in this order. Yeah. So you're like, so again, you can't put all those zeros in your calculator and you'll run out of lines, so it won't let you put them all in. So cut it down by putting it in the exponent form. So you start, if you're doing it this way, you're still going to make your number so that it's between 1 and 9. But here, I've got to go to the right in order to get to a whole unit value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so there's 20 zeros in front of that 0, in front of the 183. So this would be 1.83. So you always make your number so that it's between 1 and 9 times 10 to the negative 21. So a negative exponent indicates it's a very small number. A positive exponent indicates it's a very large number. You look, oops, sorry. See the difference between them. Now, does everybody know how to put that in your calculator? So if you have a graphing calculator, you may have learned like to use a little caret to do your exponents. There is actually a button on here that will put in times 10 to the. Does anybody know what that is? It's a single button, and math teachers never use it. I don't really understand it. Look for a button on your calculator that is capital E, capital E. So it looks like this. It's on these calculators, it's like its own button, and like you don't even have to hit second or anything. See that one? That means to put it in exponent form.
Is that the same one right there?
No, it is. Hold on.
Cause I hit that button.
Times 10. Yeah, I mean, it might be. That might
And I
be, or
just put
times
the
10 to the
negative.
n.
Yeah.
So in this one, see that? The EE, the capital E, that actually will put, you put in your whole number, so like if I was gonna write that, I would put in 1.83, then I press the EE, and when I do, see how the two little zeros come up? So it'll automatically, yeah. It actually, then, it means times 10 to the. So now I can put in my exponent values if I have to make it positive or negative, it's that button. Okay, so if you're gonna get a calculator, if you're not gonna use your graphing calculator, if you're gonna look for one, like, I really like the Texas Instruments, I think they're really great, easy. And see, they have that button straight on there. So all I had to do is put 1.83, then that EE button, and then I could put 21, and I can make it negative, so that would be times 10 to the 21st, or negative 21st. Okay, it's just a simple one, so it's that button. See how it looks? So when you get an answer in this, it won't say times 10 to the, it'll give you like a regular looking digit and then give you two little small numbers up in the upper right corner, and that's indicating that that's actually the exponent value. Okay? So that just goes over like what is the different exponents. What does it mean if you have a positive exponent? Remember, that means that you have a number larger than 1, and it's by the number of zeros. So in this one, they had, like this one's 1,000,000, and so they say it's like 10 times 10 times 10 times 10, 6 times, so that was where they get the 10 to the 6th. And then when you get to the smaller numbers, you have the negative exponents. So I did a couple like this. If it's a whole number value, give me the exponent. If it's in exponent form, write out the long form, okay, on this one with each of these examples, just to make sure that everybody can like move them and count them that way. Write them out. If it's for the first 6, it's put them in the exponent. For the last 3, it's to write them out in the long form. So if it's a number bigger than 1, just move the decimal place, count the number of exponents that you're going. You can drop the non-significant zeros. So like in the first one, those ending 4 zeros, you can drop those off because they're lagging zeros with no decimal, so they're not considered significant. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.20568 times 10 to the 9th. So it's the number of zeros that you had, the number of decimal places you had to go to make your number between 1 and 9. And you drop off any lagging zeros, and you would also drop off leading zeros if there is a decimal. 12,500 to the 4. Yep. Sometimes it doesn't really help. Like this one, it doesn't really make your number any better because at either end you have non-zero numbers. So this would be 4.5600025. Remember, zeros in between, you've got to keep those. You wouldn't leave those off. Times 10 to the... This one. Which way you're going to go? Got to go to the right by... Gonna have to go 3 places. So you'll go start at the decimal place 1, 2, 3. Since it's smaller than 1, that's a negative exponent. So see the difference between the upper ones and that one. Negative exponent tells you it's smaller than 1. Notice that I dropped the zeros off in the front. Leading zeros are never significant, so they get left off when you do scientific notation. What about this one?
4.51 times 10 to the -6.
Okay, what about those last 2 zeros? Why? It's a decimal, so yeah. They need to stay. They are considered measured values because of the decimal. Remember, lagging zeros are only significant if there is a decimal place. So those ones do have to hang out. Boy, that's a whole lot of zeros. 1 times 10 to the what?
14.
Okay, thanks. So hopefully you should see 14 zeros. So this one, you're going the other direction. So put that in expanded form. So 9.5123 times 10 to the 6. Decimal place goes which way?
To the right.
To the right. How many places? So 9, 5, 1, 2, 3. Add 2 zeros. I had to go 4 to get to the end of the 3 and add 2 more zeros. So that's not a decimal place. Comma. 9,512,300. Ooh, 1.123 times 10 to the 12.
1,123,000,000.
1, 2, 3, 4, 5, 6, 7, 8, 9. Million, billion. That's trillion. 1 trillion.
Trillion.
Yeah. Yeah. So when you have billions of trillions, it's billions of trillions. And then this last one. So this last one, which way are you going?
To the left.
Yeah, because it's a negative exponent, make sure you start off with your numbers over. Slide them over when you go to draw them because you're going to have to put 5 zeros in front of the 9 to move that decimal place -6. So with numbers like this one, like this one, like this one, it really is useful to be able to put it into scientific notation because it just shortens how much space it takes up. It's much easier to put it in the calculator. And when we get into using these numbers with molecules and pH and things like that, we'll go back over how to put things in as an exponent in your calculator. So that's why, like, if you get one or if you have one, always make sure you sort of slip it in your bag so that you can practice when we're here. So that when you get home, you're not like, oh no. Okay, so sort of an extension of this measuring is what it means in terms of percent. So we will talk about percent solutions this semester, but when you have a percent grade, so if you take a test and you get 87 out of 100, then you get your test back and it's not usually written that way. They say it's 87%. Okay, so that is what you got divided by how many points you could have gotten. I used to teach with somebody, though, that would actually write exams based on the amount of material he covered. And so he had big exams and small exams. Sometimes he'd write an exam that was 7 pages long because he had covered a lot of information. And sometimes his exams would end in 3 because he hadn't covered as much. Yeah. So these students would, so he was like, oh, I gave a 600-point exam. So that means you could have gotten 600 points. So you get your test back and you got a 512. And so then people are like, well, wait a minute, what is that? Like, because everybody's used to on a scale of 0 to 100. So percent's nice because it does that. You put what you got divided by the maximum possible, multiply it, because this is going to now be a fraction or a decimal value. Multiplying it times 100 puts it on a scale of 0 to 100. So you can compare. So in this one, times 100 tells me that I got a what percent? 512 divided by 600. Yeah, so I got an 85.3. But then, what if you only took a 270-point test and you were like, oh, I got a 210. So you like actually missed less than you did on the last one. So what was your average? 78. Jeez. Okay, so knowing, like, if it's not on an automatic 0 to 100 scale, that's what this can allow you to do, is it can allow you then to compare those two numbers. So in this one, you have 48 coins, 12 are quarters, 20 are nickels, 10 are dimes, the rest are pennies. So what's the percentage? What's the percent of quarters? What's the percent of those coins that are quarters? Okay, and you did that by what? Yep. And then multiply your answer times 100. So 12 divided by 48 is going to come out as 0.25. It's always going to come out as a decimal. So multiplying that times 100 puts it on a scale of 0 to 100. I know you just did that in your head, but that's why I'm like, so think it out, like in each case. So when it doesn't automatically work out in your head, then you're like, I know how to do this. So if 20 are nickels, then that means doing the math quickly on your calculator. About 42% are nickels. 10 are dimes. 10 divided by 48. Should have put that times 100 on the last one. 21, half as much as the nickels. And the rest are pennies. So how do you figure that out?
Add all the percentages up and take them from 100.
You could do that. Okay, or you could subtract from 48 the numbers of all of the other ones and end up coming up with how many are actually pennies. Either way, you should still come up with the same, because that would be the whole. So the whole would be 100, so all your percentages added together should give you that. Okay, so sometimes you can use this, and we'll go back, we're going to actually use like percent yield. So we're going to make aspirin in lab, and then you get to figure out, well, how much did I make compared to how much I think I should have made? So did I get a good yield, or maybe not so much? So we'll talk about how that ends up affecting experiments. So here's two infants in the perinatal ICU, PICU. One's weight has changed from 126 ounces to 147. The other's weight has changed from 86 to 103. So when you first glance at them, which one do you think has actually changed the greater percent?
86.
The 86? So you think the 86 looks better, okay? So do the math. So what you want to do is you want to figure out the change in weight. So how do you do that? Come on. Okay, so you're going to have to change in weight. You're going to have to subtract. Okay, first, so what I want to know is, what is the percent of weight change? So I went from 126 to 147. 147 minus 126. So this baby did what? Gained what? 21 ounces. And what am I going to divide it by? Their beginning weight or their ending weight? They started at 126. It's really their beginning weight. So it is what percent of weight change from their initial. So you take their 126 and multiply that times 100. Then you're going to do the same thing for baby 2. How much did baby 2 weigh or gain? 17. So gain 17 ounces and started off at 86. So that percent change. Mm-hmm. 17 and 17 divided by 86. Yeah, 19.7 or 20. So in this one, and looking at numbers, my measured numbers, 126, 147, 86, 103. When I did the subtraction, then the division, so in looking at like significant figures, I would definitely not use more than 3 significant figures in my answer. And because I had that 86, I'd probably round everything to 2, okay? Because the 126, 147, 103, those are all 3 significant figures, whereas 86, and my change is 2 significant figures, so we'll say 17% and 20%. But still, yeah, so second baby, even though they didn't weigh as much, their percent change oftentimes can be more significant than the fact that they gained 5 ounces or they gained 15 ounces. What was their starting point? And that shows a greater change in the smaller one. So in your measurements, I want you to try and be accurate and precise. And there was like a pre-lab question. If you're in the lab on campus, there's a pre-lab questions that's got a question about this. Accuracy, this is really being right. Like getting the standard number or the desired number. So I always tell people, if you're going to be accurate is almost like a one-shot deal. So if I want to be accurate, I go up, I take the bow and arrow, and I shoot the arrow, and it lands right in the middle of the target. And I'm accurate. But I only really do it once. And I'm like, there, done. So that would be accurate. Precision is being repetitive. Being able to do something consistently. Accuracy can sometimes be luck. Okay? Yeah, you like don't know what you're doing. And you're like, oh look, I just hit it. In Greenville, they have like the hatchet throwing place. I haven't been yet. But so you have like people have drinking beer and throwing hatchets. I'm like, I don't know, axes. I'm not sure that's the best plan, like all the way around. But they like are throwing them at targets and stuff. And it's really, really interesting, just the styles of the way people throw and the force that they try to throw and just how different those numbers can be. But if you are accurate, it's really just that one shot. Like you throw it one time and see. But precision is, can you do it over and over and over again? Okay? Precision is having technique. Being careful in your measurements in lab, making sure that if it says put 5 drops, that you put 5 drops instead of 15 drops or a dropper full because you weren't really paying attention. Because I had a few that like I got them back, I was like, you put a lot more than 5 drops in that speaker. But that was last week. But having that precision, that'll also end up affecting your outcomes. Because if you don't have careful technique and trying to make sure that you're measuring the amounts that are described, then you may end up with poor percent yields. You may not end up with what you're trying to make or the amount that you're trying to make. So if you are just accurate, you would hit the bullseye. If you were precise, though, you would hit the same part of the target over and over and over again. So you, in theory, you could do this. And you would say that that person has a high accuracy and high precision. So that's both. That they have good technique and all of their equipment works perfectly, so they're getting the right answer. But then I've also seen this. What does that mean? Yeah, that's low accuracy because I'm not hitting the bullseye, but I'm hitting the same spot over and over. Okay, so it may be like you can be very precise, but have low accuracy. Most of the time, that's because of your equipment, that maybe the balance is off. Okay, so there may not be the right equipment, or the equipment may need a little tweaking. So you can have that, but you really want to try and stay away from this. Because you would say that is, yeah, that's low precision and low accuracy. So you're like all over the place. Optimally, you have high. But really, as long as you have good precision, that's really going to give you the best long-term results, the best view. So we've talked about mass. We've also talked about volume. So mass and volume together, mass being sort of the amount of a substance, volume being the three-dimensional space that it takes up. And one that I'll just mention is when we think about volume in liters, and then we talk about milliliters, milliliters oftentimes volumes that you're giving in syringe doses. So if you're giving an injection or if you have IV drip rates, you might be trying to give them milliliters per minute, milliliters per hour, amounts of volume of medication. But a milliliter and a cc, which is a cubic centimeter, or a cm cubed, all the same unit. Okay? So by definition, if you had a little cube and it was 1 centimeter tall, 1 centimeter wide, and 1 centimeter deep, it would hold a 1 milliliter volume. So those are actually the same units. So if you've talked about syringes of cc's, so you have a 3 cc syringe, that's the same thing as a 3 milliliter syringe. So they're both the same units. It's just a way of like being able, and in fact the same unit size. It's just a way of being able to write one versus the other. One in length and one in volume, just by taking length, width, and depth in terms of getting that volume. So you will see that. But a characteristic that pure substances have is what's known as density. And density takes in the amount of mass something has divided by its volume. So it's mass per volume. So one of the things that I brought a couple of things to show you. So this is one. So it's a pretty thin sheet and it's bendy. Okay, so it's this gray kind of sheet. You can bend it, don't care or anything, but you can bend it. It's not harmful or anything, but it's lead. So it's just a rolled sheet of lead, but you can kind of feel it's heavy. It's got some substance to it. So lead has a pretty high density, which means that it has a lot of mass for its volume. And I should have brought like a little sheet of aluminum, because the two of them, you know what aluminum foil feels like. Aluminum foil is like weighs nothing, but you can feel that that has much more substance to it. So when trying to determine definitions, they found that if they took 1 gram of water and it has a volume of 1 milliliter, then 1 gram per 1 milliliter gives water a density that became kind of a standard value. So water has a density of 1.00. Anything that's less dense than water, if it doesn't dissolve in water, what is it going to do? If it's less dense, it's going to float. If it's more dense, then sinks to the bottom. Okay, so like your rocks and most of your metals are more dense. Things like wood is their example, less dense. It actually has a lot of little air pockets in it, and that's the reason that it'll float. But if we know the mass and the density of a substance, we can figure out volume. If we know the mass and the volume, we can figure out density. So we can use this formula as long as we know 2 of the 3, we can solve for it. So in this one, I have a 1 liter volume of sugar. So this can be just table sugar. And it has a density of 1.29 grams per milliliters. Determine the mass of the sugar in the sample. So in this, you're given there's like 3 parts to density. We know that density equals mass divided by volume. So in this, which of these units do we know in the problem?
Density.
Okay, so we know that density is 1.29 grams per mil, and we know volume, 1.00 liters. So that means this is our unknown. So mass, determine the mass of the sugar in the sample. That's the unknown. So mass is what I want to know, so I need to get it all by itself in the formula. I've always found that it's easier to move a formula around and then put the numbers in. So I want to know M. So what do you do in an algebra problem if you want to get something all by itself? What do I have to do? If D equals M over V, and I want to get M all by itself. Both sides by? If I multiply both sides by M, that's going to give me M squared. It's going to give me a whole lot of M's. What do I need to do? I want to get M all by itself.
You put density
If I multiply both sides by V, what will that do on the right? So anything in the denominator, I can move to the other side by putting it in the numerator. Okay, so here, see how volume and volume will cancel? If you have units in the top and the bottom, they will cancel. And so that tells me that mass is equal to volume times density. So you will just rearrange. All you have to do is rearrange the problem to get the unit all by itself that you want. And you can always move any unit to the opposite side of the problem. How do you say that? As long as it's on the top or the bottom? So if it's over on the bottom on one side, it goes in the top on the other. So you call that. Yeah, I don't look at it as cross multiplying. Because I see what you were saying, because you said put D over 1 and cross multiply them. And in this one, it's really, if it's in the denominator, it goes in the denominator on the opposite side. If it's in the numerator and I want to move it, I just move it to the denominator on the opposite side. As long as it is opposite side of a problem, as long as it moves from the denominator to the denominator, or vice versa. Right? Denominator is the bottom one, numerator's on top. Yeah, something like that. There was a word I was trying to think and I couldn't think what the term meant. That's why I was like, and you call that something. Just move it to the opposite side, but always make sure it just goes on the other. Okay? So we'll actually use this with just about every formula type of thing that we use. We'll end up having to do that. And it's really just a simple way to get M all by itself. Because now I can just plug in density and I can plug in volume and I know what my answer is in mass. So we know that density is 1.29 grams per 1 mil. So G per ml, it means it's over 1. So I can turn it into a fraction so that I can multiply it times 1.00 L. So when I Multiply these two together, density times volume. Do units cancel this way? I have grams, I have milliliters, and I have liters. So liters and milliliters can't cancel. So that means that I have to change a unit. I have to either convert 1 to liters or I have to convert 1 to milliliters. I've got to put volume in the same units. So in this, liters is one of my units, so I know it's only one step. So I have a base unit in the problem, so I can do this in one step. What unit goes on the bottom? Liters. Milliliters goes on top. In front of milli, you put a 1,000. So 1 liter is 1,000 milliliters. So now I can use that number. So I can use this here. So I'm going to do 1.29 grams per milliliter times 1,000 milliliters. Now you can see milliliters and milliliters will cancel. Volume times density is going to allow those units to cancel, giving me an answer in grams. 1.29 times 1,000. Mm-hmm. 1,290 grams. How many significant figures in that number at the top in 1 liter? 1.003. Okay. Density is 1.29 grams per mil. 3. So I want to make sure that my answer has 3. And it has 3 already, so I'm all set. Because that lagging 0 at the end doesn't have a decimal, so you can just leave it as it is. So I have 3 significant figures. Okay, so we'll try another one of these on Wednesday night, like when we go and pick up with that. We'll do that one. So if you've got your, I've done the, if you have your PowerPoints, like if you print these ones, these print out as well. So you've already got the written ones down, so you don't have to try and write it down. We use density when looking at concentrations of solutions very commonly in health sciences. So they may use it in a urinalysis. So urinalysis, instead of calling it the density of urine, they talk about it in terms of specific gravity. So specific gravity is really just the density of your sample divided by the density of water. And the density of water is 1. So what it really allowed you to do is it allows you to just take the units out. So instead of talking about it in grams per mil, the specific gravity is typically just a number. So it can be a really small number, like it could be 1.001. That's a specific gravity that's almost the same as water. That would be very dilute urine. That would be urine without a lot of waste, urine without a lot of salts, urine without a lot of sugar in it. So if someone is drinking their half gallon of water a day, then you might be finding this, okay? You might be seeing the real dilute urine. But if your patient comes in and they're dehydrated because they've been sick, or they're diabetic and they haven't been taking their insulin, then they may have huge solute numbers. So they could be, like kind of normal is somewhere around, say, 1.015. That's sort of normal. There are some salts, because when you start to dissolve salt into water, it's going to make that water thicker. It's going to make it more dense. So the higher the specific gravity, the more salts. Possibly the more sugar, especially if they're diabetic. The more waste molecules, the more urea, uric acid, those waste molecules that are found in urine. But when you start seeing specific gravity numbers that are going over 1.03, this is your amber urine. If you've had anybody that's you've been collecting and monitoring urine flow, when it's coming out and you're like, this is like brown. Like, That's not a whole lot of water. That is very concentrated. Lots of salts, lots of wastes, not a lot of water. That's a really thick urine, but that's really hard on your kidneys. And that's why they really do say you're supposed to drink 8-ounce glasses of water a day, and that is a half a gallon of water, and that's an awful lot of water. But it's because that helps to dilute these waste molecules out. So in looking at kidney function, they use specific gravity. If they're trying to determine just how many solute molecules they're finding in that patient's urine, specific gravity can come into play. Temperature. So temperature is another measurement that we'll use. Think of temperature as being vibration of molecules. So all molecules vibrate. So it's the amount of hotness or coldness of a sample. We use a thermometer. We don't use the scale that everybody else in the world uses. We use Fahrenheit. Celsius is the metric, and everything that we do in lab is all on Celsius. So with that, here's how the scales are a little bit different. So I have the Fahrenheit list for these characteristics and then the Celsius list. So these are really the four that you should be familiar with. Boiling, in Fahrenheit, it's 212. To get water to boil, you have to heat it up to 212 Fahrenheit at sea level. If you want to freeze water, you got to chill it to 32 degrees Fahrenheit at sea level to get it to go solid. Those numbers, when they did Fahrenheit, they developed a 0 degrees and a 100 degrees Fahrenheit based on environmental temperatures. So these were like the hottest days that they had in the summer. They made those the 100 Fahrenheit. And then when they had the 0, they made the 0 Fahrenheit the coldest. And so you're talking about some of the European, some more Scandinavian countries. So it does get pretty cold up there. So coldest temperatures where there are zeros, hottest temperatures where there are hundreds. But in metric actually has their scale based on the freezing points and boiling points of water. So 0 degrees Celsius is when water freezes. 100 degrees Celsius is when water boils. And so their scale is a little more scientific rather than just sort of more environmental as a basis. So in those two important numbers that fall into this range, body temperature, your body temperature, 98.6 is the average body temperature. That's 37 degrees in Celsius. Room temperature, not necessarily this room, but like what they call general room temperature. This room can like vary anywhere from 60 to 80 degrees in like a 24-hour period sometimes. But normal room temperature is usually considered 75 degrees. And that's 25 degrees in Celsius. So keep those ones kind of all in mind. Environmental temperatures, body temperatures. So with this, in order to change from one to the other, you would have to actually use a conversion unit, okay? Like a formula in order to switch. I'm not that uptight with you having to do that. Really, all I want you to do is make sure that you remember what is 0 degrees, what is 100, what are the freezing point, boiling points of water, room temperature, and body temperature on those four points for these two scales. We will talk about a scale that's only used by the physicists and chemists, and that is called Kelvin. And so this has to be used when talking about gases. So gases are constantly moving and vibrating. And so in studying gases and how they behave, you can't get gases below 0 because you can't put negative numbers into calculations. If gases are still moving, they can't have a negative temperature. So they had to figure out what is the coldest possible temperature molecules can have. And that became 0 degrees Kelvin. And that's 273 degrees below the 0 of Celsius. So they say the 0 of Kelvin is the temperature at which molecules stop vibrating altogether. So they like stuck. Then they can use those numbers. So all that it means is that gas molecules are all, any kind of calculations of temperature can be done with a positive temperature value, because otherwise your math doesn't work out. So we will mention these again because we're going to talk a little bit about gases and what happens with pressure and volume and temperature changes of gases this semester. But that's one that we'll talk about again. But just remember, so temperature is this vibrational activity. Celsius and Fahrenheit, there's two different values, and then what the standard ones are. So energy. Energy is, remember, the ability to do work. It can be energy in action, energy of motion, energy of electricity, doing things like making filaments and lights glow, or it could be potential, like the uneaten food, that's potential energy. It could give you energy to run your cells, but not unless you eat it, okay? So you can have stored energy. Values when talking about food energy, people talk about the calorie. So you talk about how many calories there are in a cup of noodles or in salads and things like that. So that's thinking about nutritional calories. But for us in metric, we will most commonly use what's known as the joule. So it's just another energy unit. So substances have an ability to absorb and release energy as they change temperature. So if you think of these molecules as like vibrating, so when they begin to slow down their vibration, it's because they've released energy. If they begin to vibrate more, it's because they've absorbed energy. So their ability to do that is what's called specific heat. Specific heat is the amount of energy a substance can absorb before it changes temperature. And some molecules or some substances have a very high specific heat and some have a very low specific heat. So a good example, water. Water actually has one of the highest. Water absorbs and releases energy and doesn't change temperature very fast. This is good because that means that as you exercise, your muscles release energy. That energy is absorbed by the water of the body, but your body temperature doesn't change really quick. You might start getting kind of red-faced. You do start the whole sweating thing, trying to cool yourself off automatically, but you're not going to have rapid temperature change. Has anybody ever been to like the Caribbean or been to okay, so like, what's it like there at night? What's the temperature?
It's cool.
It's cooler? Like, okay, so what is it like during the day? Okay, I can only tell you when I've been there. It's like 85, 86 degrees during the day, and then in the evening it cools down to 80.
Yeah, it just feels cold.
Like, what are you talking about? It's cooler. You like walk outside, you're like, okay? But that's jungle. There is a lot of water. There is a lot of humidity in the air, and so its temperature change is really not very high. If you like look at Cancun, the temperature doesn't change but about maybe 10 degrees the entire day. So it might drop down to 75, goes up to 85, drops to 75, goes to 85. Kind of like how it's been in August the last couple of weeks. You get up in the morning, you're like, oh, it's hot out here. Because it's muggy. All that moisture, all that water slows down temperature change. How many people have been to the desert? Like in Arizona. Now there, during the day, it can be 110 in the shade. I'm like, I don't know how people's cars don't just melt. It gets so hot. But then at night, what does it do?
30s.
Yeah. So, you're like, so you can have this huge temperature change. But in Arizona, how much water? None. Super dry. So there you're talking about sand. You can have water, you can have temperature changes of 50 and 60 degrees in a 24-hour period. All because of lack of water. Whereas in the jungle areas with high humidity, lots of moisture, because water has a really high specific heat, it absorbs a lot of that energy and then releases it very slowly and doesn't change temperature. Same thing with a swimming pool. Early in the springs, like you open your pool, like in May, and you get in it, and what's it feel like? The temperature. It might be 80 outside.
Cold.
It's really cold. Like, hey. So you're like, put the little thermal blanket on, okay? But how's it starting to feel now? It's like bath water. It's like, you're like, this is very refreshing. Like, water is warmer than the air is outside. You're like, bleh. But that's because water has very high specific heat. This is good because it really helps to regulate body temperature. if even alcohol, like is ethanol on there? Ooh, I have water. No, but that's the same. Ethanol has a much lower specific heat. So like if you like dab, it like evaporates really quickly and it feels cold because of that rapid change that occurs, whereas water doesn't have quite the effect. So I brought all my stuff to show you. I was going to show you like the changes in state. This really leads us to the very last topic in this chapter, which is looking at physical and chemical changes and also looking at balancing equations. So I'll just bring everything with me on Thursday. So I like made you a little example thing. I mean, I brought the lead sheet because I thought that was kind of cool. I found that in the chemical storeroom. I was like, I'm taking this with me. But we'll definitely go through and do those on Wednesday, looking at the states of matter. So you can do all the dynamic study modules for chapter 1. So that includes like significant figures, understanding matter, and the unit conversions. So there's those 3. Go ahead and work on those. You can finish them up. If you are getting started on the post-lecture homework for chapter 1, you can really do everything except the last 3 questions, because the last 3 questions are on this material, but really we've talked about all of the other stuff. Okay, so we've really got like maybe a half a lecture on chapter 1, and then we can go ahead and start talking about chapter 2. Did everybody get in and get that pre-lecture for chapter 1 done? Did anybody not? It was such a pain. I know that like My Labs Plus, beginning of the semester, they always have challenges because they like put so many students into classes. So I will open it up again until Thursday. Okay, so by Thursday, make sure you get pre-lectures for chapters 1 and 2 done, and then you can go ahead and be working on the other assignments. Okay, but I'll make sure that I do that like before I leave tonight. I will have that